Today I will introduce the basic concepts of probability theory. So, probability theory had its origins in the games of chance in early 16th and 17th century, when the owners of gambling houses in Europe, they became interested to explore that whether one can find out the probabilities of various events which take place during a gambling game, such as tossing of dice, rolling of coins, roulette wheels, etc. So, they contacted some of the prominent mathematicians of that time, say Pascal and Fermat, and through the correspondence between these mathematicians, the theory of probability started to develop. One of the fundamental features of this probability is that the phenomena which we are interested in are random in nature. So, for example, if you consider tossing of a dice, then we do not know whether which face bearing number 1, 2, 3, etc. will come. But in the long run, if we toss enough number of times, then the proportion of the number of occurrences of say one of them, say 6, will be 1 by 6, say, then it means that the probability or the chance of appearance of 6 is 1 by 6. Similarly, in the tossing of a coin, we do not know that at each trial whether we will get a head or a tail, but if we toss a large number of times, then we know that nearly 50% of the times there will be head, or 50% of the time there will be tail. This long term behavior is known as statistical regularity, and that is what encourages us to study the subject probability. A similar kind of observation you can make in the experiments which are connected with the real life, such as experiments in physics, experiments in genetics, or virtually any phenomena in real life. Consider, for example, birth of a offspring. Now, suppose we consider human beings, then for each birth we do not know whether the child will be a boy or a girl, but in the long run it is very well known what percentage of children will be boys and what percentage will be girls. A insurance company, while promoting a new policy, would like to know how many of the people will survive up to the age of maturity. For example, if the policy matures at the age of 60, then it would like to know the percentage of the people in the target group who will be surviving beyond the age 60 and therefore may get the benefits which are due to them. Now, for individual person, it is not possible to tell whether he will die at the age of 60 or not, but in the whole population one can tell the percentage of people dying before 60 or dying after the age of 60. A similar kind of statistical regularity is observed, and it is used for weather predictions, the prediction of the, say, growth of crop, the economic growth, the financial situation of a country, etc. Here what happens that in most of these cases, although the things may look that they are preordained or predesigned, but predetermined, but actually there will be several conditions which regulate the occurrence of the final phenomena, and therefore one can treat them as random phenomena. Now, we will introduce some of the basic concepts. The first is experiment, the term which I have used repeatedly just in the discussion. So, an experiment is observing something happen are conducting something under certain conditions which result in some outcome. Let me explain this little vague definition. So, consider say rainfall. So, now rainfall is a consequence of several things. Finally, we observe that there is a rainfall. So, there is a cloud formation, there is some El Nino currents, there is a humidity, there are various factors which lead to there is a rainfall, or there it is cloudy, or it may not rain at all, it may rain in some other region. Now, observing of this weather is a experiment. Similarly, suppose we consider how much crop of a particular, or how much yield of a particular crop, say wheat is there in a particular field. Now, this is dependent upon the seeds, the plot of the land where it is there, the irrigation procedure and other mechanical procedures which are used for farming. So, the entire process, although we are not conducting, but it is happening and it is a random experiment. The outcome is recorded as the final yield of the crop. You must be very well familiar with a lot of experiments which are done in physical, chemical and biological sciences. For example, we have various experiments in chemistry where certain chemicals are mixed and they result in some compound being made. So, broadly speaking, we segregate the experiment into two types of experiments. One is deterministic experiment. In the deterministic experiments, under certain conditions, if an experiment is conducted, it results in a known outcome. So, many of the classroom experiments in physics, chemistry, biology, etc., they are like this. For example, if I have two molecules of hydrogen and a molecule of oxygen, then we know that the outcome is a water. Suppose we consider, say, we put water in a vessel and heat it. When the temperature reaches 100 degrees Celsius and the atmospheric pressure, say 700 mg, then the outcome is that the water will boil. So, these experiments are called deterministic experiments. However, we are not concerned with these experiments in this subject of probability. We are concerned with the experiments which are called random experiments. In the random experiments, although we may fix the conditions under which the trials are conducted or the experiment is conducted, but the outcome is still uncertain. Consider, for example, tossing of a coin. So, although we may fix a lot of conditions such as what kind of coin we are having, how to hold it when we are tossing, but even then when we toss the coin and it falls, the outcome is uncertain. It may be head or tail, or in some extreme situation we may consider that it stands on its side also. Consider, say, tossing of a die. So, again the conditions are similar. We may fix the die in various ways, but when we toss it, and if it's a if we are really tossing it, then after falling which face will be upwards is not known. Suppose we consider drawing of a card from a deck of cards. Suppose we consider, say, birth of a child. Suppose we consider age at death of a person. Suppose we consider, say, amount of rainfall during a monsoon season in a geographical area. Suppose we want to consider yield of a crop of a certain food grain in a state. Suppose we consider the time taken to complete a 100-meter sprint by an athlete. All of these phenomena, here the conditions of the experiment are fixed. For example, when we look at, say, the time taken to complete a 100-meter sprint by an athlete, then the conditions are fixed. For example, the ground is fixed, the starting time is fixed, the athlete is in a perfect condition, the person who will direct the race is prepared, the person who will record the time is prepared. However, how much actual time the sprinter will take to complete the 100-meter race will always be uncertain. It may be 10 seconds, it may be 10.1 seconds, it may be 9.7 seconds, etc. Suppose we are considering, say, a mechanical instrument such as, say, life of a bulb. So, when you purchase a bulb from the market and you light it, then it may work for 1 hour, it may work for 10 hours, it may work for 100 hours. So, although all these bulbs may be produced by the same company under the same conditions, even then the actual life of the bulb is not fixed, it can vary. If we look at, say, working time of a say, life of a mechanical instrument, say, for example, a certain turbine or a certain engine. So, although they are all produced by a certain standard process, but the actual life of that instrument cannot be predicted in advance. We may consider, say, in these cases, all of these examples, they relate to certain fixed conditions for the conducting of the experiment. However, the final outcome is not known in advance. So, all of these are known as random experiments, and in the subject of probability, we are concerned only with the discussion of the random experiments. So, for example, if we why these type of events are of interest. For example, you consider birth of a child or age or death of a person. So, now these phenomena are extremely useful in practical. For example, insurance companies, when they propagate a life insurance policy, they are very much interested that what premium they have to fix. Now, how to decide about the premium? The company charges a premium, and in the case of unlikely case of the person dying before the age of maturity, he has to be paid full benefits of the policy and plus some assured sum. Whereas, if the person completes the policy, and that means he does not succumb before the age of maturity, then he pays the premium till the maturity, and then he gets certain benefits which or not that much as he would have got if the person had died before the age of maturity. Therefore, the company has to estimate how much premium it will be charging and how much will be actually the cost to the company in the event of the death of the person prematurely. So, the age at death of a person in the target group is to be estimated, and therefore, we will record, we keep the records of the ages of the persons in that particular target group for which the company is trying to sell the insurance policy. If you look at the amount of rainfall, then extremely important phenomena, because there are a lot of policies of the government, the policy, agricultural policy, the economic policies, which are based on actual rainfall which is going to be there in the country. The yield of a crop makes the government to decide about how much food grains they are going to purchase from the farmers, how much they are going to store, what should be the price which should be given to the farmers, what should be the price for the market. So, all of these events, the experiments, although they do not look random beforehand, however, outcomes are not known and therefore, they are random, and in the subject of probability and statistics, we do study these type of phenomena. So, now let me introduce certain basic terminologies of the random experiments. The first of this is the concept of a sample space. So, the set of all possible outcomes of a random experiment is called a sample space. The usual notations we will use either capital omega or capital S, etc., to denote the sample space. So, let us consider some examples. Suppose we are considering tossing of a coin. In the tossing of a coin, we may put the outcomes we may consider as head or tail, and if we denote by H the occurrence of head upwards, or by T the occurrence of tail, then the sample space can be described as HT. If we consider tossing of a die, then the sample space we may describe as occurrence of the face uppermost. So, the sample space will be the set of the numbers 1, 2, 3, 4, 5, 6. If we are considering a drawing of a card from a deck of cards, now in a deck of cards there are 4 denominations: heart, club, spade and a diamond, and each card has a value 1 to 13. So, if we consider drawing of a card, then it will consist of the set, for example, diamond 1 to diamond 13, club 1 to club 13, heart 1 to heart 13, or a spade 1 to spade 13. So, the sample space consists of 52 points. If we look at, we may also observe the sample space in a way, like for example, we may only record the color of the. So, in that case we may describe it differently. We may call this one as omega 1, and if I am recording only the color, then it may be say black or red, or we may only record the denomination, that is whether it is a heart or whether it is a diamond or it is a club or it is a spade. So, the sample space will consist of only 4 points. This also shows that sample space is not a unique thing. In a given experiment, what we are interested in will decide that what is a sample space. If we are looking at the birth of a child, then it is a vague statement, or you can say a vague way of describing what is a random experiment. Now, we may record whether the child is a male or a female child. We may record whether the child born has is healthy or not healthy. So, we may put it as healthy or unhealthy. We may look at his body weight at the birth. So, the body weight may be some number starting from say 0 to say maybe 10 pounds. It may be the total life of the child, So in that case this may be something like say 0 to 100. So it depends upon that what is our actual interest, and we can write the sample space accordingly. Age at death of a person, so this may be say 0 to say maybe 120, keeping into account that there are some people who live very long, where this unit of the time is years. Amount of a rainfall may be recorded in say centimeters. Yield of a crop may be recorded in some metric tons. The time taken to complete a 100-meter sprint may be a time from say 9 seconds to say 11 seconds. Suppose I am considering an international field. Life of a bulb is a number say which is 0 to infinity, although theoretically speaking it is not infinity, but it can be a large number. Life of a mechanical instrument similarly can be described. Suppose we are looking at the number of defective items produced by a company. A particular kind of items we are looking at, suppose we are looking at certain bolts, then what will happen that we will define the defectives, that if they do not conform to certain prescribed standards of measurement. So now the number of defectives may be recorded in terms of percentage. So the percentage can be say 0 to 100%, or it could be say proportion. In that case we may write the number as say 0 to 1. So the sample space will again be dependent upon the way we want to look at it. Next we define what is an event. An event is any subset of the sample space. Now this is a very broad definition, and therefore any subset of the sample space qualifies to be an event, to be called an event as far as the probability theory is concerned. So let us look at the experiments now and the examples that we have already done. In the first case, if we look at omega is equal to ht, we may consider a subset as consisting of only h. We may consider a subset consisting of say only t. So the set A denotes that head has occurred, the set B denotes that t has occurred. So these are events. We may consider say the set E in the case of tossing of a die, we may write 2, 4, 6. This means occurrence of an even number. In the birth of a child, suppose we are looking at say weight at birth in pounds, and suppose we say E is equal to 4 to 8, then it means that the birth weight of the child is between 4 to 8 pounds. If we look at the amount of rainfall and in centimeter during a particular monsoon season, and we may put say 50 to 75, that means the actual rainfall is between 50 centimeter to 75 centimeters in that geographical area during that particular monsoon season. So any subset of the sample space can be considered as an event. Now we have various kind of events. For example, impossible event. Since every subset is a subset of every event is a subset of the sample space, therefore the empty set phi, that is a subset of omega, therefore this will correspond to impossible event. Similarly, we have sure event. Since omega itself is a subset of omega, therefore this is denoting the sure event. For example, we may consider tossing of a die, and we say that 7 occurs. So that will correspond to an impossible event, because 7 is not a subset of this, and that will correspond to phi as far as this random experiment is concerned. Suppose I am looking at the age at death of a person and we say 1000 years, then it is an impossible event. Suppose we say time taken to complete a 100-meter sprint by an athlete, and we may put the time as say 5 seconds. Then in the present circumstances or present age, this is an impossible event. Similarly, if I put that the time taken to complete a 100-meter sprint by an athlete, provided he completes the race, is less than 1 minute, then this will be a sure event. If we look at the life of a bulb and we say it's a positive number, then or a non-negative number, then it's a sure event. So these are two you can say extreme types of events which are possible. However, there are various set theoretic operations like unions, intersections, differences, complementation, and therefore given any two events, when we take their unions, intersections, differences, complementations, etc., they must correspond to certain events, and we can describe them in the form of probabilistic explanation. So, for example, union of two events. So, what does union of two events implies? That if I say A and B are two events, then A union B, this will mean occurrence of at least one of A and B. That means either A occurs or B occurs or both occur. So, in set theoretic representation, A and B, A union B means that the set of elements which are either in A or in B or in both. In probability theory, the event A union B will indicate that at least one of A or B has occurred. Similarly, we may consider union of a n events A1, A2, An. Then this will mean occurrence of at least one AI, I is equal to 1 to n. We may even consider an union of infinite number of events, union AI, I is equal to 1 to infinity. This will mean occurrence of at least one AI, I is equal to 1 to infinity. Intersection of two sets denotes the set of all those points which are common to the two sets. Now, in set theory, that is the representation. In probability theory, A intersection B will mean the simultaneous occurrence A and B. That means both event A and B are deemed to have occurred. Similarly, we can consider intersection of n events AI, I is equal to 1 to n, that is simultaneous occurrence A1, A2, An. That means all of the events A1, A2, An occur, and in a similar way intersection of an countable collection of events A1, A2, etc. Here, when we consider the unions or the intersections, certain basic properties are there. For example, we may have union of AI, say I is equal to 1 to n is equal to omega. That means all the points of omega are contained in one or the other of the AIs. Such events are called exhaustive events. So, if A1 union of AIs is equal to omega, we call A1, A2, An to be exhaustive events. Here in place of n, we may have an infinite collection of events also. Similarly, if A intersection B is equal to phi, now in the set theory this means disjoint sets. In probability theory, A intersection B is equal to phi denotes that the events A and B cannot occur together. They are called mutually exclusive events. A and B are called mutually exclusive events. That means happening of one of them excludes the possibility of happening of the other. We may also consider something like this, that we have a collection A1, A2, etc. of events such that AI intersection AJ is equal to phi when I is not equal to j. Then we say that A1, A2, etc. are pairwise disjoint or mutually exclusive events. Given an event A, the A complement will denote not happening of A. In a similar way, if I have event A and an event B, then A minus B will denote happening of A but not of B. This is true because this is equal to A intersection B complement. That means simultaneous occurrence of event A and B, which means that A occurs and B does not occur. So it is a simultaneous occurrence of A and B complement, and it is translated to occurrence of A but no occurrence of B.